So, welcome you all. This is the 13th talk of Astrophysical Talk series organized by Istanbul University Observatory. And we have an exceptional speaker today, Alessandro Patruno from Institute of Space Sciences in Spain. He got his PhD degree in astronomy from University of Amsterdam in 2009. Actually, if you are working on a high energy astrophysical era, especially with X-ray data, you must know him very well. So we thank you first for accepting our offer to give a talk here. So it's your turn, Alessandro. You can start sharing your screen.
Okay, thank you very much for the kind introduction. Let me share the screen. Okay. Do you see it?
Yes, it's perfect.
Thank you. Okay, so thank you for the invitation. It's really nice to see this, many of you again after several years locked in the house. The talk of today is about extreme phenomenon in accreting millisecond pulsars, in the sense that I want to overview what is our understanding of these peculiar systems, because there are many news that occurred in the last decade, I should say. And so I've split the talk into three parts. First, I will focus on neutron stars in low mass X-ray binaries, which are basically the bigger family of binaries among which there are accreting millisecond pulsars, and talk a little bit about the mystery of the sub-millisecond pulsars that we have never seen so far. And then move to the main topic of this seminar, which are the transitional millisecond pulsars, which are this relatively new class of possibly accreting binaries that switch between radio and accreting states. And then I will try to make a connection between transitional millisecond pulsars and accreting millisecond X-ray pulsars and see whether the two systems are the same or there is a more substantial difference. So let me start with some introduction on the neutron stars in low mass X-ray binaries. What are the open issues? What do we know? Well, first of all, I talk about low mass X-ray binaries because the formation channel for fast rotating neutron stars occurs only via low mass X-ray binaries. You start with the. Do you see my pointer, by the way? Do you see the mouse when I move it?
Yes.
Yeah, okay. So you start with a binary where you have a high mass star and a low mass star. The high mass star dies and forms a neutron star, possibly a radio pulsar. And after several millions or billions of years, there might be an accreting phase where the rush lobe of the donor star is filled and there's mass transfer and you have the low mass X-ray binary phase. It is in this phase that some of these low mass X-ray binaries show X-ray pulsations, in which case we talk about accreting millisecond X-ray pulsars. And then the idea is that this accretion process terminates, and then you are left with the millisecond radio pulsar and the leftover from the accreting from the donor star. Now, this is what is called the recycling scenario. That, of course, was you all know that this was first originally proposed by Ali Alpar and by Radhakrishnan and Srinivasan in '82, and explains why in the so-called PP dot diagram of radio pulsars, you have two big clusters of young, normal, slowly rotating pulsars with high dipolar magnetic fields of the order of 10 to the 12 Gauss, and this group in the bottom left where there are millisecond rotations and low magnetic fields of the order of 10 to the 8 Gauss. So during this recycling phase, somehow the neutron star during the accretion must turn into these different systems. Now, this was the picture that we had until a few years ago, because then there was a new discovery, which are the transitional millisecond pulsars, which are systems that have been observed in principle, and I'm very careful here, between an accreting phase where they behave as accreting pulsars and a radio pulsar phase where they behave as radio millisecond pulsars in binary. And these systems switch back and forth between these states every few years. Now, when you are in this low mass X-ray binary phase, so this will be the second part of my talk. Now, I want to focus on these systems to understand what is known about them. In these low mass X-ray binaries, you form an accretion disk where you have the neutron star in the center. And there are typically two length scales of the problem. The first one is the so-called magnetospheric radius. The magnetospheric radius is the distance where the dipole field, which is not a dipole anymore, of course, because there's plasma, but where the magnetic field, basically the magnetic field energy density or the pressure becomes dominant over the plasma pressure. And so the plasma now follows the magnetic field lines and lands on the surface of the neutron star. And then there is another radius, which is called the co-rotation radius, where you have the rotation of the plasma in the disk is equal in angular frequency to the rotation of the neutron star. Now, the idea is that if the co-rotation radius is somewhat outside the magnetospheric radius, the plasma that attaches to the magnetic field lines spins faster than the neutron star, so its specific angular momentum is higher, and you spin up the neutron star. So this is the idea of what should be happening in these low mass X-ray binaries. Now, it's important to observe them for many different reasons. Understand how fast they spin, of course, has astrophysical implications, has plasma physics implications. But personally, let's say, what drives my research is to try to find the fastest spinning objects, because in this case, you can constrain, for example, the equation of state of ultra-dense matter is called. This is an example of a mass radius diagram of neutron stars. And here, these curves correspond to different solutions and compositions for the neutron star. We don't know what happens in the core of neutron stars because we don't have an understanding of the strong force at high densities and low temperature. This is something we cannot reproduce in heavy ion collisions on Earth. I mean, the density can go up in a heavy ion collision when you collide, for example, two lead atoms or gold atoms, but the temperature is pretty high, so we cannot study this matter when it's cold, and the only place to check it is by looking at neutron stars. And if we can measure mass and radius, in principle, we could constrain the composition in the center of these objects. Now, the rotation is important because rotation gives you a limit where the centrifugal force of the object would exceed the gravitational pull. And so you would exclude certain areas. For example, this curve that you see here corresponds to a rotation of 700 Hertz, which is more or less the fastest known spinning a neutron star. But you see that the constraints are not great because basically almost any mass and radius for the neutron star are allowed. So we still don't know whether the composition is stiff or soft. So if there are new particles that appear or they are mostly neutrons, protons, muons, and electrons. For example, by finding a very fast spinning object, say a rotation of 1200 Hertz, one would exclude this huge area in the mass radius diagram. And then, for example, in this case, you would say, oh, this must be an equation of state of this the soft in this case. Of course, there are many curves that corresponds to many solutions. This is just an example. Now, the problem is, and the question is, why don't we just take radio pulsars, because we know thousands of radio pulsars, and then why to look into low mass X-ray binaries? And the reason is simple. In low mass X-ray binaries, these objects in principle should be the fastest because there is a slowdown phase when the accretion ends. And so in principle, if there are, the fastest neutron stars should be in accreting objects. Now, the problem is that these accreting millisecond pulsars, there are very few, there are about 20 known. But we know like something like 150, 200 low mass X-ray binaries with the neutron star. And so there is a huge population where the spin is unknown. So if you take the number of neutron stars in low mass X-ray binaries, only about 20%, like 15% have a known spin. And it's a really big mystery why they don't pulsate. Most low mass X-ray binaries with neutron stars don't pulsate. The possibility is that this is related to some weird behavior of the magnetic field. Now, another interesting fact is that if you take the neutron stars in low mass X-ray binaries, for which we know the spin distribution, you can calculate just a histogram of the spin distribution, the density function, the probability density function. And then what you see is that this distribution stops here, where you have the fastest known objects that in X-rays, in the accreting systems is about 620 Hertz. And then there's nothing here above this frequency. And again, there is a problem because in principle, these systems should exist. Fast spinning objects should exist. Also, there was a discussion in a recent paper from Reitmakers et al. In 2021 that considered the latest constraints on the equation of states that imply a 12.3 plus minus 0.8 kilometer for a 1.4 solar mass. And if you take this constraint and you translate it into a maximum centrifugal force that the star can sustain, that the neutron star can sustain, you get that it is certainly larger than 720 Hertz, which is the fastest radio millisecond pulsar found. So this is very perplexing. Also, this distribution is quite interesting because even if the number of objects here is pretty low, you can try to model it with, for example, with two gaussians. In this case, this distribution was modeled with the two gaussians. And then you can find, doing statistical tests, that there is a significant cut point, which is the frequency, basically, that divides the two distributions. So one might wonder, but can this be one distribution only? Yes, but you have a more significant statistical test if you use two. And basically, what you see, and here is pretty flat. So it's not even that Gaussian, of course. But again, the number of objects here is small. It's about 10, 15. Sorry. But what you see, the important point here is that you see two subpopulations in the neutron star low mass X-ray binaries with the known spin. One that seems to be slow and one that seems to be fast. And there is a very sharp peak at around 500-600 Hertz. Why there is this peak is not known. This has implications because, of course, it could tell you that there is some mechanism slowing these objects down. For example, we propose in this paper the possibility that gravitational waves kick in. But of course, until we have a detection from LIGO or Virgo, because there are no detections of continuous gravitational waves at the moment, or they're only from mergers of compact objects, as you know, then we cannot know whether this distribution has this fast population as this limit because of gravitational waves. Now, so the picture, the take-home message here is, the picture is already quite complicated for low mass X-ray binaries alone. If you take a neutron star in low mass X-ray binaries, there seems to be two subpopulations. Most neutron stars don't pulsate. We don't know why. And we don't see sub-millisecond pulsars. So there must be something wrong or incomplete, I should say, in our understanding of how this recycling works. Now, in 2009, something happened, and there was a new class that was discovered among accreting binaries, which is the class of transitional millisecond pulsars. Now, this new class has complicated, in my opinion, enormously our understanding of what's going on in low mass X-ray binaries, because it has introduced new ingredients and new behaviors that are very difficult to explain with our current understanding of how the astrophysics works, the physics works. So these systems, for those of you that have not heard about them, are basically systems that switch between an accreting state and a radio pulsar state. This object called Pulsar J1023 plus 0038 is the first the first transitional millisecond pulsar discovered. This is a binary. It has an orbital period of about 5 hours. There's a neutron star, which is a millisecond radio pulsar. It's 1.7 millisecond spin period. And the companion is a subsolar star, is 0.2 solar masses. Now, this object was discovered as a radio pulsar. Sorry, it's not true. This object was seen as a radio pulsar and was seen to spin down as all radio pulsars do because of loss of angular momentum due to the emission process. But then people went to look for archival data and they found something strange. Basically, this object that was discovered as a radio pulsar in 2007 had some archival observations in optical taken in 2000, 2001. And what people saw is this very strange spectrum. So in 2007, the optical spectrum was matching the spectrum of a G5 dwarf star. So this is the typical spectrum that you see in binaries when there is no disk. But then in the 2000 observations, there was a continuum that corresponded to a disk, an accretion disk. And furthermore, there was also an H-alpha emission line with the typical double horn, which is due to the Doppler motion in the disk. And so people believed that this had been a low mass X-ray binary in 2000, 2001, and then in 2007, this was observed as a radio pulsar. Now, it's important to say that in 2007, there was no trace whatsoever of a disk because there was no H-alpha emission line, there was no residual disk. These disks are easy, especially the H-alpha line. It's very easy to observe if there is even a tiny amount of material that is rotating here. The funny thing is that when this object was a radio pulsar, so when it was discovered in 2007, this object belonged to a radio pulsar binary class known as redbacks. These redbacks and another type called black widows are basically millisecond radio pulsars that are ablating the companion via strong pulsar wind. And the star is not in Roche-Lobe overflow, the companion star, but is very close to. So this was interesting, and I mention it because there might be a relation between these classes and transitional millisecond pulsars. Now, the observation showed in June 2013 another state change. So basically, in 2007 was a radio pulsar, and then it was continually observed throughout 2013 in radio. This is the orbital phase from 0 to 1. These circles represent radio detections in different orbital phases and different times. And then at some point, here you see the crosses, which are non-detections. These are due to eclipses, due to basically there is an ablation from the companion, and then you have free absorption of the radio waves in the free electrons, like the plasma that surrounds the system. So it's normal to have some non-detections in certain orbital phases. And then at some point in 2013, during a sudden period of time that lasted a few days, the pulsations disappeared in radio and were never seen again. And there was a large increase also in gamma rays. This is the Fermi-Lat curve between 1 and 300 giga electron volts. You see that there is an increase of a factor of a few during this transition. So this object turned back. The idea is that turned back into a low mass X-ray binary. The Q that you see here is there to say that this object had a very low X-ray luminosity that corresponds to the quiescent phase of low mass X-ray binaries. So luminosity is of the order of 10 to the 33 ergs per second. Now, the observations were also done during the radio pulsar state in the years before, during these years. And people modeled the X-ray light curve. And what they saw is that during the radio pulsar state, there was a strong irradiation of the companion star. Here, these two rectangles represent basically the shock that is close to the inner Lagrangian point. And you see that there is a small asymmetry that probably was observed also in the light curve that is compatible with the fact that the neutron star is irradiating the inner Lagrangian point. Here there is plasma that tries to flow from the Roche lobe filling companion and then leaves the system on one side because of the angular momentum of the orbit. And during this state, the optical observations showed no disk whatsoever. So this is the timeline of this object. It was a radio pulsar and then turned into a quiescent low mass X-ray binaries, then again a radio pulsar, and then turned back into this quiescent low mass X-ray binary phase that is still active today. Now, we have to be careful because this quiescent low mass X-ray binary phase looks very strange. If you look at the X-rays, this is the light curve of taken with XMM in 2013, and you see this very strange light curve where there is a low, so-called low mode that corresponds to a luminosity of 10 to the 32 ergs per second. Then there is an intermediate luminosity called high mode, 1 order of magnitude brighter. And then there is a flaring mode, which can reach another order of magnitude more in brightness. So there's this very, very fast flickering on time scales of minutes, basically. The idea initially was that because the subluminous state corresponds to typical luminosities of 10 to the 33 ergs per second, which are very common among quiescent low mass X-ray binaries, then this would be a quiescent low mass X-ray binary. This was reinforced by the fact that when we looked at the X-rays, we found pulsations. So we found pulsations, X-ray pulsations during the quiescent low mass X-ray binary state. So we thought, okay, then the plasma, as I explained, is flowing through the magnetosphere, hitting the poles, and then we have accretion-powered pulsations. And there were no radio emission. So here, there's no radio emission. If you look for radio, the radio pulsations are gone. This makes sense because radio pulsations, the idea of radio pulsations is that this might be curvature radiation. So you have electron bunching is called. You have little clumps of electrons. And if the length of this clump is smaller than the typical wavelength of the emission, then you have coherent emission. Basically, the electrons behave as a supercharge, and they emit, if you take the Larmor power, it's proportional to the square of the charge and the square of the acceleration. And if these electrons are moving all together, the square of the charge is n times the square, everything squared. So it's very powerful. So it's a coherent. And this bunching is destroyed, the idea, when you have accretion, because there's a lot of plasma flowing on the magnetic, along the magnetic field lines. So it's normal to not see a radio pulsation. Then when this object clears the disk and the plasma for some reason that is mysterious, then we see the radio pulsations. The other interesting thing is that these pulsations were seen only in this high mode when the luminosity was 10 to the 33 ergs per second. The pulse fraction was substantial, about 8%, and there was nothing detected in the low mode and in the flaring mode. And this is not a statistical problem because the flaring mode is much brighter. So there were no pulsations. So we thought this might be related to intermittent accretion pulses. So maybe the accretion stops for some reason at some point. Another very weird observation that we did was the discovery that when you calculate the spin down in radio, due to, this is what every radio pulsar does, spin down of radio pulsars. And when you measure the pulsations, these pulsations here during the X-ray phase, you can compare, you see also spin down during the X-ray phase, but this spin down during the X-ray phase is 20% larger than what is seen in radio. This is very difficult to justify, as I will show you in a moment, because the radio spin down, the idea is that when the system is a radio pulsar, the spin down is due to magnetic dipole radiation, basically, and you lose angular momentum and energy in this way. And accretion spin down instead should be due to the fact that the plasma interacts with the magnetosphere and somehow extracts some of the angular momentum, perhaps because the corrotation radius is closer than the magnetospheric radius. Or maybe there are other mechanisms, maybe gravitational waves. We considered this in 2017, although I don't believe this is probably is not correct anymore, because for timescale reasons. But in 2020, sorry, I forgot to say, these observations were made with XMM between 2013 and 2017. Now, there was a group in Padua led by Burtovi et al. They found pulsations in optical, and they measured these pulses with the AQI plus instrument. This is an optical photometer, very fast, with a very fast sampling time. So they could measure the pulsations in optical, and they could find a timing solution. So they calculated the frequency at different epochs between 2019 and 2020. And they found something very strange. They found that the spin down that they see is only 5% faster than in radio, not 25%. So we found 25% with an error of 8%, and they found 5% only. So the idea is that perhaps there's a significant variation between epochs, because our observation were between 2013 and 2017, and this was in the 3 years following this. Because there should be no reason why in different wavelengths you see different spin downs, because optical and X-rays, as I will show you now, are supposed to come from the same mechanism. I mean, the neutron star is spinning down, it's generating this pulsation, so you should see the same spin down. Now, I have to mention that these objects have a tremendously difficult and erratic orbit. It's very erratic. The orbit moves up and down, so it's very complicated to model the orbital variation. So this, I would not exclude that this difference, both here and here, is partially due to systematics. So keep this result in mind with some, with a bit of skepticism. Now, going back to what, let's say, what it seems to be established is that during this accretion phase, the spin down is very similar to radio. That's, let's say, not controversial. Then the amount by which this spin down exceeds the radio is a matter of debate, but it's very similar. And now this should not be the case, because if you take, for example, a propeller occurs when, again, the rotating plasma touches the magnetic field lines, but it's rotating slower than the neutron star, and then the magnetic field. So the magnetic field acts as a sort of merry-go-round and boom, kicks the plasma out. So if you take a propeller, a strong propeller, it means simply that magnetospheric radius is at least 1.3 times larger than the corrotation radius. So there's a substantial difference between the rotation in the disk and the magnetosphere. Then this material, as you very well know, carries away angular momentum. If you jump on a merry-go-round, the merry-go-round will, the turning will slow down and you will be kicked out. And this spin down should not be related to the radio spin down, because these are two completely different mechanisms. So this seems to require substantial fine tuning. Another model that was proposed by Parfrey a couple of years after this transition was this model where you have an accretion disk. Now, this is a resistive disk. When you have a resistive disk, what happens is that the magnetic field lines penetrate the disk, and then as the magnetic field opens up because of rotation of the disk, you basically open some magnetic field lines. So here in blue, this is the rotation of the neutron star. In blue, these are the field lines that are open when you have a radio pulsar. That's because at some distance, this dipole must open up because of the rotation of the neutron star, and the magnetic field lines need to rotate faster than the speed of light. So they open up. But when you put a disk, many more lines open up, and they form this sort of separatrix here between magnetic field lines connected to the neutron star and those connected from the disk to infinity. And the spin down that you expect in a resistive disk is proportional to how many of these field lines you open. And now, so this, but then the number of field lines that you open, this psi open, is basically given by this parameter, this zeta parameter, which tells you how efficient the disk and the magnetic field are coupled. And long story short, if we want to explain just a 30% increase in spin down, 25% increase, or even 5% from the Italian group, we need an incredible fine tuning, because the number of open field lines, which should not depend, that depend on the accretion physics and are unrelated to the number of open field lines in the radio, need to be very similar. So this psi open should be anything between 1 and 10. So it's very strange. This is also a model that requires fine tuning. Now, there is evidence, however, that there is an outflow, maybe even a propeller, in the sense that if you look, this is the X-ray light curve that I showed you before. This is from Chandra, actually, it's not the one. This is the one before was XMM, but this is the same object, flaring, high mode, low mode. And then we took a VLA simultaneous observation, so in the radio band. And what you see is that these two light curves are almost perfectly anticorrelated. And usually radio increases when you eject plasma because of synchrotron or different mechanisms that create an outflow. So this is something well known in X-ray binaries. So this seems to suggest that there is something that is being expelled in the system and has to do with whatever mechanism is producing X-rays. Now, there's another interesting thing, which is in 2017, Ambrosino discovered optical pulsations. And this brought some questions to the picture, because we don't know optical pulsations from any other accreting object. And the pulse profiles were double peaked. It was a very strong detection. There was no doubt about it. They proposed a synchrotron emission, but how is this compatible with what we see in X-rays and in radio was still open to debate. Then last year, we discovered ultraviolet pulsations in the same system. And this is the, well, I should say the second, but let's say when we found it was the first system, the first pulsar that shows ultraviolet pulsations. This is an HST image. These are the pulses. I have to say the detection was relatively marginal. So this is about a 4 sigma result. So it's not super strong. But if confirmed, this UV and the optical pulsations might be related to synchrotron emission. But then what about X-rays? Are X-rays coming from a complete different mechanism, maybe from accretion, and then optical and UV are coming from synchrotron emission? Well, the answer is no. They probably, the X-rays probably are not a good tracer of accretion for the following reason. This is a diagram as the spectral energy distribution of Pulsar J1023, the same object. This was published 3 years ago by Papito. So what they found was they did something very smart. They took the X-rays from XMM, the pulsed emission from the X-rays from XMM, from NuSTAR that goes up to 79 kilo electron volts. And then they coupled this with the optical detections from the TNG. This is the Telescopio Nazionale Galileo. I think it's a 3.5 meter optical telescope. And they found that optical soft X-rays and hard X-rays are all lying on the same power law with a spectral index of minus 1.3. So the idea is that this means probably that the optical X-rays, soft and hard, are coming from the same mechanism. Now, what it means is unclear. There are different interpretations and possibilities. One possibility that was discussed is that the accretion basically is not really ongoing, and maybe there's a pulsar wind that hits the inner part of the accretion disk and generates radiation. But this is still open to debate. Now, of course, the question is, what about other systems? I should say that we know only 3 transitional millisecond pulsars. There's a 4th one, which is this one. It's a candidate because its light curve in X-rays resembles very strongly the other systems. And this one is interesting because it has also radio emission, and we did a radio observation quasi-simultaneous with XMM last year, and we published the results. This one that you see here is the radio X-ray luminosity diagram. This is a very well-known diagram for people that work in X-ray binaries. What you see here is the following. There are black holes, which are these circles in quiescence. So these are black hole in low mass X-ray binaries, and they all lie more or less with some scattering, of course, on a straight line. This is a log-log plot. And then underneath, you have neutron stars with the squares. The blue squares are neutron stars in low mass X-ray binaries. And when we did the observation of these objects, what we found is that these 4 big circles are the 4 known transitional millisecond pulsar, with this one in red, which is the candidate one. So what we saw is that their radioluminosity is very powerful, and it lies on perhaps closer to the black holes than to where they should be according to neutron stars. But let's say the picture is quite confusing, because if you add accreting millisecond pulsars, they seem to scatter a bit everywhere. So again, here the take-home message is these objects, transitional and accreting millisecond pulsars, seem to be both powerful emitters of radio waves, incoherent, of course, this is not the pulsations, which are correlated with X-ray luminosity. So there must be some sort of outflow and some connection between the X-rays and the radio. But again, the picture doesn't tell us exactly what's going on. Now, what is the connection between the transitional pulsar and the accreting millisecond pulsar, if there is any? And I want to show you just a couple of very interesting things. The first is about the optical and UV pulsations detected in 2021 by Ambrosino in this system, SAX J1023. This is an accreting millisecond pulsar in a low mass X-ray binary. This was the first one discovered in '98. And this is at least until now, beyond doubt, an accreting system. It is accreting because it shows very powerful, this shows powerful outbursts. Here you see the count rate versus time. This is an outburst. The luminosity here, the peak luminosity is a few times 10 to the 36 ergs per second. And there is accretion on the surface for sure, because we also see thermonuclear X-ray bursts due to the compression of the accreted material on the surface of the neutron star that triggers hydrogen or mixed hydrogen-helium thermonuclear explosions. Here in these 2 diagrams, you see power spectra that refer to an observation made very early during the onset of the outburst, and another one pretty late when the outburst was almost finished. So optical pulsations are there together with X-rays. And the interesting thing is that Ambrosino could demonstrate that the pulsation in optical was coming close to the region of the neutron star, so it was not due to irradiation. Now, this object, X-J1023, is known also to be overluminous in quiescence with respect to X-ray radiation, and so the idea was that this turns on as a radio pulsar maybe sometimes, but we did a very deep radio pulse search in quiescence, and we did a campaign in 2014 with Green Bank, and there was no radio pulsation detected. The upper limits were very strong. The question is this behaving in quiescence as a transitional pulsar? Does the pulsar turn on also in these systems? It's difficult to say, but one key observation that was not published, I think, is the spectrum. This is an optical spectrum of J1023, and this one is the double horn H alpha line. So this is there's clearly some residual disk in quiescence. So this system, if it turns on as radio, it's strange because in the transitional millisecond pulsars, they don't show any evidence for a disk, whereas here there is evidence that there is a disk. Now, the very final thing I want to say is I mentioned these bursts in J1023 to say the following, that we do know that the magnetic field and these objects are relatively dipolar, in the sense that we do see pulsations coming during the thermonuclear explosions too, which suggests that some of the burning is confined, and we have evidence that the plasma remains in the magnetic field lines. Now, it's a bit late, so I'm not going to explain this picture, but what I want to say is that bursts confirm that there is accretion on the surface during outbursts. So these are accreting objects, at least the accreting millisecond pulsars, the classical ones, let's say. And the field is relatively dipolar. So what is the connection between these two objects? The connection between transitional pulsar and accreting pulsar is unclear. That's the conclusion, let's say, in the sense that all these observations seem to have some common behavior, but then the transitional pulsars seem to be poorly related to the accretion process, in the sense that the X-rays are not necessarily tracing the accretion, whereas in accreting millisecond pulsars they are. The Roche lobe completely clears up from plasma in transitional millisecond pulsars, whereas in accreting millisecond pulsars this is not seen, at least in one case. And the magnetic field in accreting pulsars seems to be relatively dipolar and stable. And so the conclusion is that maybe transitional millisecond pulsars are really not accreting, and it's a particular phase of the evolution of binary pulsars in general, whereas the accreting millisecond pulsars are still in the low max X-ray binary phase. What exactly is happening, we don't know, but the question is open, and we will see with further observations. And this is it. So thank you very much for your attention.
Thanks a lot, Alessandro. So we have time for a couple of questions. If there is, we can take them. Yeah, Mehmet Ali Alpar. Ali hocam.
Just a moment. Hi, Alessandro. It's great to see you here.
Yes, I was mentioning you before. Nice to see you again, Ali.
Yes, I have comments. First, on the first part of your talk about the existence of an explanation for minimum equilibrium period for Spindown pulsars. I'd like to point out this paper that Unal and I published, a short paper last year, where we use Dipankar's and Sushan Komar's early results relating the m dot in the LMXP phase to the final frozen field by field diffusion through the crust. There's a correlation, and if you put their fits that Sushan and Dipankar produced into the standard formula for the equilibrium period, you do get a clear minimum. And we intend to continue on that to try to deconvolve the spin period distribution with that idea to see what it implies for an underlying distribution of the m dot b. That's just a comment. But,
I agree with you. I just to make a comment. I didn't talk about magnetospheric disk interaction in the talk for for reasons of time. But yes, I also believe that it's very possible that this is solvable with something like that.
Yeah, I mean, there's a different physics reasons for why one reaches a minimum period without having to involve gravitational radiation or such. That's the first comment. The other comment, if Ünal is here, I don't know if he's here, he might make it, concerning the second part of your talk.
Yes, I am here.
Yes, because I mean, he has this whole view of really carefully reassessing where the inner radius of a disk is, covering both strong and weak propeller phases and accretion phase and spin up and spin down. So it's some not so simple combination of the effects of the Alfvén radius, but more dominated by the location of the co-rotation radius, and then one doesn't really need so much fine-tuning to get some of the aspects, but Ünal himself is here.
Yeah, I very briefly dived into models because, as you say, indeed, there are many other possibilities. I tried just to give a possible observational overview, let's say, but you are right. Of course, there are these models. There are several other possibilities. There's even the famous trapped disk that we were working on a while ago. So there are different combinations of physical parameters that are poorly constrained that give rise to models that might, in principle, explain what we observe. But yes, so you are right. Yeah.
Well, anyway, this was a very, very nice talk, and there's a lot of very interesting stuff in the transitional binaries. So we should be in touch, and maybe you can come visit us physically.
Of course, and also vice versa, of course. Yes. Yes, we should. Thank you.
I think, Ünal Hocam, you might contribute something.
Yes. Hi, Alessandro.
Hello. Hi.
It was very nice talk. And I want to ask about these transitional millisecond pulsars, their quiescent states. You said that there is no evidence of disk, partly because of lack of this H-alpha emission. Is there any other evidence that we can 100% sure say that there is no disk during the radio pulsar phase?
That's a good question. To my knowledge, from observational point of view, there's not a lot. The only thing I can say is that if you look at the X-rays, you see also some X-ray emission, but at lower luminosity, and it's very stable in the sense that this comes from irradiation of the donor, because of course the disk has much faster time scales. So probably that's an indication, but I would say it's a weak indication. So besides the H-alpha and this, I would say, or I don't know any other evidence for lack of plasma in the. I mean, another indirect evidence, if you want, is that the radio pulses are there. So if you want to keep this electron bunching, it's hard to imagine if you have a lot of plasma around the neutron star. That's another possibility to constrain the geometry and the plasma in the system.
I ask because if the propeller mechanism starts at that time, both the truncation of part of the inner disk and the outgoing plasma can prevent observation of this H-alpha emission. This is first point. Second, related to presence of radio emission, you know, in the new picture of the magnetosphere, the field lines outside the magnetosphere is open.
Mm-hmm.
So this is similar to the light cylinder radius in the case of old models. So it is very reasonable, I think, to expect radio emission, radio pulses even during the propeller phase, when the inner disk radius is inside actually the light cylinder radius. This could be the case, I don't know.
Yeah, it could be. It could be that there is a region that, I agree. It's possible. I mean, depends on the model, of course, the details of the calculations, but yeah.
Okay, thank you very much.
Thanks a lot. So there's another question. Sharon Hocam, buyurun.
Yeah, we cannot hear you.
You have to unmute yourself.
Okay, I'm sorry. Sorry about that. I started my video, forgot to unmute myself. Okay, just a very quick question. With these transitional pulsars and that particular example you showed, which has low mass X-ray binary characteristics and so forth, as I understood correctly. And so I only wondered if, because you never showed anything, or maybe I missed part of your talk actually, that was there any study using broadband noise characteristics, comparing the broadband noise characteristics in the lowest state, let me say, to the intermediate one and to a higher level, and compare that to spectral changes, like the standard way of spectral timing study? Was that done? Because that helps to understand what happens if there's a disk, no disk, what happens to the disk?
Yes, of course. Yeah, it was done. Actually, the power spectrum is pretty featureless. You see a red noise components, and that's it. And in this, and this is for any of the states, of course. For the spectra, the spectrum doesn't change. So you do the energy spectrum of low, high, and flare modes, and the spectral index stays the same, which is very strange.
Yeah, that is. So if there are some changes without the spectral change, plus also the power spectrum doesn't seem to change. The broadband noise in general, let's think about that.
There is nothing. There's just a red noise. There's a power low that goes up to whatever.
And there's no cutoff, like there's no break or no nothing?
No, I mean, it goes down to high frequencies, but that it's not, I forgot now. There is a frequency cutoff, but I forgot. It's stable and it's a few hertz, but I forgot. I have to look at it. But it was published.
It doesn't show changes, basically. That's that very strange thing. Yeah. No. Okay, thank you. Thanks a lot.
Okay, is there any other question? So it seems not. So we thank Alessandro Patruno again for this very nice talk and for all the audience for contributions. So see you on our next talk then.
Thank you very much, and have a nice week. Thanks again.
Thank you. Thank you, Alessandro.
Bye.